Ever wondered how engineers design machines that move with precision, like the gears in a watch or the arms of a robot? It's not just about bolts and screws, it's about solving a mind-bending puzzle. Today, we're diving into a groundbreaking AI tool called MechaFormer that's revolutionizing how we design mechanical systems. Imagine you want a machine to trace a specific path, say, a perfect circle or a wavy line. Traditional methods, they're like trying to find a needle in a haystack. Why? Because designing these mechanisms involves balancing two tricky things: discrete choices, like how many joints a machine has, and continuous variables, like where those joints are placed. It's a huge, messy search space that's hard for humans or old algorithms to navigate. Enter MechaFormer, a model that treats this problem like a language translation. Instead of guessing, it learns to read a target curve and write a set of instructions, a special code called a domain-specific language, DSL. This code tells the machine exactly how to build itself to match the curve. And here's the kicker. It does this in one go, figuring out both the structure topology and the details geometry at the same time. Think of it like teaching a robot to draw. You show it the shape you want, and it doesn't just guess. It learns the rules of how to build a mechanism that can replicate that shape. But how does it handle the chaos of so many possibilities? MechaFormer uses a transformer architecture, similar to the AI that powers your phone's text predictions. But instead of words, it works with mechanical tokens. Here's the magic. It normalizes all the data by anchoring on key points, like the base joints of a mechanism, stripping away unnecessary details. This lets the model focus on the essential geometry, making the problem manageable. And the results? This model doesn't just match curves, it surpasses existing methods. It generates a wild variety of valid designs, some of which are totally new. Plus, it's not just a one-trick pony. By combining its outputs with traditional optimization tools, engineers can refine solutions faster than ever. So what's the big deal? MechaFormer isn't just a tool. It's a bridge between human creativity and AI efficiency. It's like giving designers a superpower to explore thousands of ideas in seconds, unlocking innovations we couldn't dream of before. Next time you see a machine moving with precision, remember, behind the scenes, AI like MechaFormer might be helping it learn the dance. Thanks for watching. If you're curious about how AI is reshaping engineering, hit subscribe for more deep dives into cutting-edge science. And let me know in the comments, what kind of mechanical design would you want a computer to create for you? Until next time. But let's take a step back. While MechaFormer represents a leap in generative design, traditional optimization methods still play a critical role. Take L-BFGS-B, a classic algorithm used to refine mechanical systems. Think of it as a precision tool for fine-tuning. Imagine adjusting a car's suspension to smooth out every bump on a rough road. Here's how it works. L-BFGS-B treats the design problem as a mathematical optimization. It starts with an initial guess of the mechanism's joints and iteratively tweaks their positions to minimize a dynamic time warping, DTW score, a metric that measures how smoothly the machine's movement matches the target path. It's like solving a maze, where every turn must align perfectly with the goal. But there's a catch: constraints. For example, engineers might fix certain joints to simulate a robot's feet staying planted at 0 and 10. These rules act like anchor points, ensuring the solution remains physically plausible. The algorithm settings, like maxiter equals 50, limiting iterations to 50, and ftol equals 10.6, stopping when changes are minuscule, balance speed and precision. It's a delicate dance between exploration and efficiency. The result? A mechanism that moves with surprising efficiency, proving that even the most complex problems can be tackled with the right mix of creativity and computation. Whether it's AI-driven generative design or classical optimization, the future of engineering is a collaboration between human ingenuity and machine intelligence. So what's next? As these tools evolve, they'll unlock new frontiers in robotics, biomechanics, and beyond. Stay tuned for more deep dives into the science that's shaping tomorrow's machines. Until then, keep questioning, keep exploring, and remember, the next great invention might be just a few lines of code away.